All right, let's jump right into this. If you're studying A-level geography, you already know mastering this topic is just absolutely vital. Today's explainer is all about the Earth's life support systems, or ELSS. We're going to blend the epic scale of global observation with some really rigorous academic analysis. We're talking about the intense dynamic equilibrium of our environment and how on Earth we actually measure the massive changes happening right beneath our feet and, well, high above our heads. So let's get into it. Now, the first thing we really need to nail down is exactly why we're even doing this. We aren't just out here collecting data for fun. Observing long-term changes to our water and carbon cycles, that is literally the only way scientists can accurately advise our global governments. And that advice directly informs the laws and policies we absolutely need for climate mitigation. Without accurate monitoring, we're essentially just flying blind in a massive storm. So here's our game plan for today. We'll quickly establish the mission, look at our orbital sentinels, drop down to the ground vanguard, evaluate how they clash, and then bring it all together in an ultimate synthesis.
Part 1. The ELSS mission. First, let's establish the battlefield here, which is the fragile dynamic equilibrium of our planet's carbon and water stores.
When you look at our Earth's life support systems, you're looking at a total masterclass in dynamic equilibrium. It's this incredibly delicate balance between stores and flows in our water and carbon cycles. But as we know, human factors act as powerful catalysts that severely mess with this balance. From aggressive forestry and urban expansion to draining deep aquifers and the relentless burning of fossil fuels, we're altering these natural processes at a speed we've just never seen before. And to manage that, we absolutely have to measure it. Which brings us to Part 2, orbital sentinels. To track these massive planetary scale changes, humanity has deployed advanced satellite remote sensing. Meet our first sentinel up in orbit. This is NASA's Orbiting Carbon Observatory 2, or OCO-2. This satellite is a marvel. It's engineered specifically to gather massive datasets on global carbon sources and sinks. It basically gives us a planetary view of exactly where carbon is being absorbed, like by vegetation and oceans, and where it's being emitted by industrial combustion and wildfires. Honestly, it's like a giant high-tech stethoscope just listening to the planet breathe. Now, for the water cycle, we rely on IceSat-2. This one precisely measures the changing ice levels at our poles. By tracking the thickness and the elevation of sea ice and ice sheets all across the Arctic and Antarctic, IceSat-2 lets researchers monitor these massive, overarching shifts in global water stores. And down in the tropics, the tracking gets even more sophisticated. The Terra-i system uses a powerful neural network to analyze satellite data, giving us dynamic, near real-time monitoring of land cover change. It scans the landscape every 16 days. If you look at those darker reds, that reveals the most recent active deforestation spreading across southeastern Colombia. It's an incredibly rapid early warning system for habitat destruction. So let's summarize the strategic strengths of these orbital tools. They give us the incredible power of immense spatial scale. We can monitor the water and carbon cycles globally and produce these vast, sweeping datasets. Plus, as we just saw with Terra-i, they offer dynamic, near real-time tracking. But, and hey, this is a critical but for your exam evaluations, they are crazy expensive to build and launch, and they notoriously lack hyperlocal on-the-ground detail. And that naturally leads us to a really crucial question for your analysis. If satellites are so incredibly powerful, what essential ground-level realities are completely escaping their orbital eye? That takes us to Part 3, the ground vanguard. To answer that question, we have to zoom way down to the surface and look at the elite fieldwork researchers operating right inside these complex ecosystems. These fieldwork researchers are literally on the front lines. Take Teri Riutta's work, for example. Researchers use these towering structures called Flux towers, which basically act like giant, highly sensitive respiratory monitors embedded deep in the rainforest. Satellites can tell us a forest is there, sure, but a Flux tower reveals the carbon sink's exact behavior on an hourly basis. It shows researchers exactly how the forest responds to tiny disturbances, which is completely essential for creating accurate tropical carbon budgets. Let's flip to a completely different extreme to see how this builds our understanding. Up in the harsh, rapidly warming conditions of the Arctic, researchers known as Team Shrub are doing vital field work. They're tracking how shrubification, which is the increase of woody plants in the tundra, alters surface albedo, changing how sunlight gets absorbed or reflected. Even more importantly, they monitor how thawing permafrost releases ancient, trapped carbon directly into global climate-positive feedback loops. You just simply cannot get this level of complex ecosystem interaction from space. But this ground vanguard has a massive, glaring vulnerability. A staggering 76% of the Earth's land surface is considered incredibly challenging for hydromonitoring and modeling. Why? Well, because these crucial areas are mostly located in low and middle income nations that just don't have the financial resources or infrastructure to maintain extensive, labor intensive ground stations. The true scale of this gap is honestly a bit terrifying. When you look at the global distribution of ground-based stations measuring stream flow, the blank spaces are massive. Out of over 130,000 global basins, less than 1% actually have runoff gauges. That leaves immense territories, especially vital headwater catchments, totally ungauged and unmonitored. Without boots on the ground, we just don't have the localized data we need in these regions. Part 4. The clash. Now it's time to evaluate these two monitoring factions head to head. This is a really vital analytical skill for hitting those top marks in your assessments. Okay, so in one corner we have ground-based observation. This provides highly reliable, incredibly detailed local data that shows us exactly what's happening beneath the canopy. But it's super limited in coverage, it's incredibly labor-intensive, and it just takes a vast amount of time. In the other corner, satellite monitoring. This gives us sweeping global data sets over immense spatial scales. However, it's highly expensive, and fundamentally, it lacks detailed verification of what is actually happening down on the surface.
And that brings us to part 5, the ultimate synthesis. This clash of strengths and limitations leads to the climax of our briefing.
I want you to consider this fundamental hinge question. It's exactly the kind of critical thinking you need for high-level geography. Do our orbital sentinels completely replace the need for boots on the ground? Or is there a much more symbiotic, interdependent relationship at play here? The crucial takeaway for your exam synthesis is that they absolutely must synchronize. Satellites provide the massive global maps we need for overarching global governance and spotting broad trends. But that data is essentially unverified. They're blind to the intricate details unless they are continuously validated or ground-truthed by highly localized, reliable fieldwork. Without Teri Riutta's Flux towers or Team Shrub's permafrost data, the satellite models could completely misinterpret the actual carbon and water fluxes. Both methods are absolutely essential. They literally complete each other. So, as we wrap up this explainer, we're left with a stark reality. We have incredible tech in orbit and dedicated vanguards on the ground. But with less than 1% of our global basins actively gauged and positive climate feedback loops accelerating faster and faster, we have to ask, as this dynamic equilibrium shifts, which unmapped, unmonitored frontier will be the next critical battlefield for our Earth life support system? It's a massive question that the next generation of geographers, which is you all, will have to answer. Keep studying, keep questioning, and I'll catch you in the next explainer.